Hello friends, welcome to YourPedia, and as you know, this is the part of the series that we have started where we are discussing with you the assignments, that is a few problems from the NPTEL assignments which are highly relevant from the GATE examination point of view. So one of the problems that I am going to discuss with you today is from machine design, and more specifically it is related to the fatigue loading chapter. So I would advise you, first of all, just go through this problem, just see the context and just try to solve it by yourself. Then you will realize the importance or the kind of depth this problem is having, and I think on these lines he may frame the questions in future also, right? So let's go to this particular problem. Just see it. What it says: a bar of steel has properties where he has given you some properties. For example, endurance limit, SE is the endurance limit, and SY yield strength, and then you are having ultimate strength as 550 megapascal for that material. Now he's saying that, let's say if I draw that bar, so let me just draw that bar first. So let's say I'm having this bar which is talking about, let us say, and the loading condition he has given over here is that it is subjected to a steady torsional load or stress of 100 megapascal. So it means steady torsional, that means static, it is not changing. For example, let's say if I am applying a torque of constant torque in one direction only. So constant torque in one direction, and that torque I can say is a steady torque or shear stress because of that as 100 megapascal. So what I am showing it with different colors. So let us say I show that with the, this is the, at one end I am showing that is a 100 megapascal is the torsional shear stress which is steady in nature. In addition to it, he is saying an alternating torsional stress of 70 megapascal. That means he is applying a torsional shear stress which is fluctuating and varying. And what is that? He is saying of 70 megapascal. It means what he is doing, in one direction he goes up to 70 megapascal as a torsional shear stress, and then he reverses the direction completely up to the 70 megapascal. So if I take 70 positive in one direction, then obviously I will say that the same bar is subjected to minus 70 megapascal in other direction, because sign convention is going to play a great role. So let us say if I show that stress, you can say you are having a one more torsional shear stress, but that torsional shear stress is what? Plus minus 70 megapascal. Not only that, he is also saying that the same bar is getting subjected to alternating bending stress. Now same is the situation over here also. So what he is doing is basically he is applying a bending stress. Let us say I am saying this way, this is the condition. That means he is completely reverse bending stresses that he is applying over here, and again it is what is 80 megapascal. So can I say this is plus minus 80 megapascal? Of course. And you can simply understand that if he is applying 80 megapascal in this direction, then if I reverse it, then obviously it will be negative in other direction. So this is the condition of loading. Now how we have to, now what is he saying? Take the factor of safety. You are supposed to find out the factor of safety against the fatigue failure, and by using the Goodman's criterion, and obviously for rounded up to 2 decimal places and all that. Now first of all, if I ask you, how do you design a component when it is subjected to fluctuating stresses, right? That means when it is having mean value of stress as well as the amplitude of the stress also. So how you design that component, right? If it is a completely reverse stresses it is subjected to, then we go ahead with the SN diagram, or we can say we design it based upon the endurance limit. But let us say it is subjected to fluctuating stresses where you are having mean as well as the stress amplitude. In that case, you make use of the three criteria, the most prominent criteria that you may have studied in machine design, that is called as Soderberg criteria, Goodman's criteria, and Gerber criteria, right? He is asking us to use the Goodman's criteria. So let us say if forget about all these, so if I simply talk about that I am having only one type of stress, I am having only one type of stress, let us say, and that is fluctuating. That means it is having mean value of stress as well as the stress amplitude. So you can use the Goodman's criteria this way. So I am drawing that one for that. So let us say this is the, so let us say on one axis you are having this amplitude of stress, and on the other axis you are having what? Stress amplitude, and on other axis you draw the mean stress. And obviously when you are having only amplitude of stress, that means mean value of stress is 0, then obviously it becomes endurance limit becomes the criteria. So on at one axis, let us say if I say this is the endurance limit, if I take that, and on the other axis when you have no amplitude of stress, that is a static stress, steady stress. So in that case we design based upon either yield strength or based upon the ultimate strength, and Goodman has taken the ultimate strength as a criteria while joining those points. So the other side is you are having ultimate, sigma ultimate, let us say. So Goodman, because Goodman is taking sigma ultimate on this side. So when we will join with the help of this, so I have this line which is joining endurance limit to the ultimate point, and this line basically gives the a limiting line to design a component which is subjected to a fluctuating stresses, that is fluctuating having a mean component as well as the mean value of stress also, using the Goodman's criteria. So this becomes the Goodman's criteria. So I will use this line for designing. Now this is a limiting line. So if I apply a factor of safety on that, then you already know. So if I give a same factor of safety on both sides, then I can have the situation like, let us say, after having the same factor of safety. So this is the same factor of safety. I am taking same factor of safety, same factor of safety. Then this point and this point becomes how much? So I will say this becomes SE divided by factor of safety. This value will become SE by factor of safety. Since I am applying the same factor of safety over here, so I can say sigma ultimate divided by same factor of safety which I am applying. So this value becomes this much. Am I clear? Now these are the two limiting points on the straight lines, and let us say if that component is subjected to, now this component is subject to a particular mean value of stress and amplitude of stress. I am denoting that with the sigma A dash and sigma mean dash. That means this is a particular value of the stress amplitude and mean value of the stress to which that particular component is subjected, had it been only one type of stress. I am not talking about this case as of now. So had it been a one type of stress, so let us say that point is this. That is, this is the value to which your component is actually getting subjected. So I am writing it as a coordinates. It is, you are going to have, let us say this coordinate sigma mean is going to sigma mean dash and sigma amplitude dash this way. This becomes a coordinate. Now if I have to use the Goodman's approach, now applying the factor of safety as well as, so then if I want to find out the, let us say, factor of safety, then how do you write the, so now you have the equation of a straight line which you can use over here. How you can use the equation of straight line? For example, if I take the coordinate for the mean value of stress as sigma mean, so I will write it this way, sigma mean dash and intercept of this on the x-axis, because sigma mean will be shown on the x-axis. So what is the intercept on x-axis of this line? So this will be sigma ultimate divided by factor of safety. So the sigma ultimate divided by factor of safety. Same way over here on y-axis we are having a other coordinate as sigma A dash. So if I take this straight line, its intercept over there is this one. So it is going to be sigma A dash divided by, you are having this intercept SE divided by factor of safety equal to 1. Right. Now you can rearrange it. So simply what you do is take it factor of safety, it can come to this side. So I can write it, rewrite it in a different way, right? Simply taking the factor of safety up and it will go down over there. So if I bring this factor of safety over there, so I am just writing it over there in a simple way. So because I have to make use of the space, so I am writing this way. So it will become as sigma amplitude dash divided by what? SE, that is the endurance limit, plus we have sigma mean dash, intercept is over there, that is sigma ultimate, and since I have taken factor of safety, it goes to that side. Am I clear? Now this was the case when, let us say, it was subjected to, let us say, only fluctuating stress of torsional shear stress, torsional only, or maybe it may be bending only. So in that case, you will say it is subjected to a particular value of mean stress and amplitude of stress. Then it is, I can directly find it out and input it over there and get it. Now, but when you are having a complex loading case in this, such as this, where not only you are having a fluctuating components of two different stresses, for example, bending stress fluctuating, you are having shear stress fluctuating, but in addition to that also have the mean value of stress, shear stress, additional component. So when I am having a different stresses and all of those stresses are fluctuating, then in that case I need to find these values as an equivalent, that for this fluctuating stress condition, what is the equivalent value of mean stress which is acting on this component. Same way, for this combination of stresses, what is the amplitude of that, to which amplitude now? This is the equivalent amplitude of, for all of these fluctuating stresses that is acting on that component. So those basically in this case now these will become what? These will become the equivalent values of amplitude, equivalent values of mean value of stress from here. And to calculate that mean values or equivalent mean values and equivalent mean those mean as well as amplitude values, I have to make use of the theories of failure to find out that. And once we are able to do that, then I think our job becomes very easy. Then simply I have to input it over here, right? So in case of a single stress fluctuating, straightforward, easy to find it out, and we can go ahead. Now let us first write down those stresses and then how we are going to find out that equivalent value of the stresses that we will see over here. Okay, so what I am doing is first writing down the stresses one by one and how to find out the equivalent that we will see over there. So first let us say I am writing this stress. Which one is the first? Is the study torsional stress. How much is the study torsional stress? So I am denoting it as a mean. Study means mean. So what is that? Let us say I am denoting it as a tau mean, which is equal to what? That is equal to 100 megapascal. 100 megapascal. Now, so okay, no amplitude of stress. Now let's go to the second one. That is this one. That is a shear stress, but fluctuating. So over here it is having maximum as well as the minimum value. So can I say that is let me say this way, sigma max, let us say 2. How much is that? You will say 70 megapascal. And same way if I say sigma minimum 2, how much is that? You will say if one is 70, then other one is going to be negative. So from here, in addition to it, I am also having another stress called as what? I am having a bending, right? And bending is also fluctuating. So can I say the bending value of stress, maximum value of bending stress is how much? Can I say this is 80 megapascal, and what is the minimum value of bending stress? You will say it is minus 80 megapascal. Okay, so let us now find out the what? The mean first. Let us say mean of this. So here I am having only mean, this one, no amplitude. Now for this I have to find out the mean. So what is the mean? So let me just write it as a mean 2. So what is the mean? This plus this, it will become 0. This plus this divided by 2. What about the amplitude? In this case, amplitude of shear stress for this is going to be this minus this divided by 2. Maximum minus minimum divided by 2. So this minus this becomes 140 divided by 2, that means 70 megapascal. Same way, I need to find out the mean for this and amplitude of stress for this fluctuating stress. So you know, if I say the bending mean is going to be how much? Is equal to this mean is going to simply addition divided by 2. So it is going to be 0, whereas bending, what is going to be amplitude of the stress in this case, then you will say this minus this, so it becomes 160 divided by 2, again it becomes the 80 megapascal. Right? That's all. But you know, since we are having mean over here, amplitude also, mean over here, amplitude also, mean over here. So what do we need to do? We need to find the equivalent mean, because I need this value of equivalent mean. What is that? I need the equivalent amplitude of stress over here. So how to find out for this combination of stress? For that, we make use of the theories of failure, and you know the most prominent theory of failure that we use is the distortion energy theory of failure, particularly for the ductile material. And since it is talking about the shaft, then obviously you can simply think of shaft is a ductile material. So in this case, or let us say he is talking about a bar of steel, then steel is is a ductile material depending upon what kind of steel it is. But okay, now once we have this, now we have a theory of failure called as distortion energy theory, and as per that distortion energy theory of failure, we can have a equivalent value of the stress. This is a general formula that we can write. So let us say if that component is subjected to different kind of stresses, let us say if it is subjected to bending, so I can say bending square plus 3 times, let us say it is subjected to shear stress, let us say, so I can say shear stress and square of that and under root. So we can, this is a simplified version of that. That means if that component is subjected to bending and combination of, let us say, torsional shear stress, or it could be happen this way also, torsional shear stress, and it could be direct normal stress also. So depending upon that, I can have this. Now from this I can find out these mean as well as the amplitude equivalent. Now when it means when I have to find out the mean, so what I will do, I will write the mean. So I have denoted it with dash, so I will say dash. Then I have to take the mean component of these values also. So bending mean as well as the mean of the stress also. Let us say if I want to find out the equivalent of amplitude for this, then what I will do, instead of mean, I will write here what? Amplitude. Amplitude of bending and amplitude of this shear stress. So that way I will be able to get the equivalent value of mean and equivalent value of amplitude stress for this combination of loading, and I can just directly input this formula and my job will be done. So I am doing the same way. Now first I am finding out the amplitude, then I will find out this. Now let me just find out the amplitude. So it is sigma a dash that I am writing, that is amplitude, equivalent amplitude. How should I write? You know, bending, amplitude of bending square plus 3 times tau, amplitude of shear stress square, this one. Now let's take look at these values. What is the value of sigma amplitude over here? I don't have, only I have sigma amplitude over here only, that is 80. And what about the amplitude of shear stress? So amplitude of shear stress exists only over here. There is no amplitude over here. So that means over here amplitude of stress combined together, this one and this one, I am having only this one, that is a 70. So can I write it this way? That means you are having over here sigma BA, that means 80 square plus 3 times tau A square, that is a 70 square under root. So that value you are going to have. Let me just see the value. What is the calculation part? So it will come out to be 140, 80 plus 3 this, so it will turn out to be 145.25 megapascal. Same way you can calculate the equivalent mean value of stress. Now instead of amplitude, now I am going to input the value of as mean, bending mean plus shear stress mean. Now tell me what is the value of bending mean? Bending mean you have 0. What about the shear stress mean? Now keep it in mind, we are having a mean value of stress over here because of this, and we are having a mean value of stress over here. So since in this case, because it was completely reversing, so it is 0, but had he given you the value, for example 70 and the other one was have been 150, something that way, so then there would have been some value of mean. But always you have to take the what? This total of that, because I am having one mean over here, another mean is over here. So combine together this plus this, because nature is same. So that means net mean for me is 100 plus 0, that is 100. So can I write it this way? 0 plus 100, 3 times 100 square So this value turns out to be, I am having 173.2 megapascal. 173.2 megapascal. That's all. So my job is done now. So I have been able to find out. Now rest I have to input these values over here. Then I will be able to find out the factor of safety that I have over here. Now just input the value. Sigma A I am having over here as A dash that I have 145.25 divided by SE, where is the ultimate, he has already given me the corrected endurance limit, which is 275 megapascal, plus sigma mean dash I have already been able to find out 173.2 divided by what? Divided by ultimate, sigma ultimate. How much is the sigma ultimate? 550, which is equal to 1 by factor of safety. Right? Now from here I can find out the factor of safety. And what is the factor of safety? I think we are able to get 1.186. 1.186. That's all. So this is going to be my answer. Now he can manipulate the same question in different ways. So I think in the fatigue loading chapter, the most complicated kind of situation that he can create is, I think, this kind of example, where on the similar lines he will manipulate. See, in simple case, let us say if I had given you let us say bending stress, fluctuating bending stress, let us say it is fluctuating from 60 to what? Minus 180 megapascal. Let us say, had I given you that way simply, then it was simple because it is fluctuating. He is asking to calculate factor of safety, let us say by using the Goodman line, a Goodman diagram. Then you will find out the sigma A dash for this, because this is maximum, this is minimum. So you will get sigma A dash from directly from here, sigma mean dash from directly from here, and directly input the formula, in formula you will get it very easily. For one stress, when only one stress is fluctuating, whether it is a torsional shear stress, whether it is a shear stress or axial stress or bending stress, then straightforward. Find out the amplitude, find out the mean, get it solved, very, very easy. But when these components are varying, this is also varying, this is also varying, and this is also varying. So what to do? In that case, we have to go for the theory of failure to find out. In that case, the same thing will become equivalent. They are going to become the equivalent value, and that equivalent value of amplitude and mean, you have to find it from the what? Distortion energy theory of failure, where we have a simplified equation for different loading conditions over there. Use that once we have been able to find out, and then you can find it out. Now how you can manipulate further? What he can do is, instead of giving, like he has given you a steady torsional load or torsional stress, he may give you varying torsional shear stress, he may give you varying axial stress, and he may give you steady bending stress. Now when he will give you steady bending stress, simply you need to add that, like we have added it over here, this one, this. Simply we need to add the components, because you know tensile stress is going to be either bending stress is going to be, steady bending stress is going to be not either positive or negative. So he will give you the value. So simply you need to add it to the axial stress, as simple as that. And for the torsional fluctuating shear stress, you simply find out the mean and amplitude as we have done over here and do it. So any of these component he can just manipulate, right? So you simply need to just write them separately and then use this, and then you can find out this. So I think you may have found it relevant from the exam point of view. I think there are so many other questions in NPTEL assignment also, where they have in past also they have directly framed the questions from there, and there are some questions, very good quality questions I am going to discuss with you in the coming days. As you know, almost on daily basis we will be uploading almost 1 or 2 questions over there to discuss with you, so that you have the holistic assessment of the quality of the questions that you have in NPTEL assignment from the GATE perspective. So okay, so that is all for today. So see you in the next session. Till then, bye. Thank you.